This lesson is on radioactivity. You'll find it in your textbook in chapter 21. We will be including it in our chapter 3 test though because it is related and we only need to know a small piece of that chapter. So radioactivity was discovered by a man named Henri Becquerel. You'll notice this text is in green. In this PowerPoint, everything in green is what you need to write down in your notes packet. Anything in black you do not need to record. So Becquerel was the first person to study radioactivity, and it started with a a technique people knew is called phosphorescence. Phosphorescence is the spontaneous emission of light from a substance after it's been activated by exposure to light. So you may have had little toys that if you held them up to a lamp for a while and then turned the lights off, they would glow. This is phosphorescence. Photo paper reacts with this, so you expose it to light, it's going to react, and you're going to see different things happen depending on the type of paper. So he actually came upon, discovered radioactivity by accident. He was doing an experiment, and he was testing the link between X-rays and phosphorescence in a photographic plate. So he had a hypothesis that when he took the photo paper and when he exposed it to uranium and the sun, that it would phosphoresce, so it would glow. What happened was he didn't have the sun though one day. It was cloudy when he was trying to do his experiment. And so he took the photo paper and he took the uranium and he put it in a drawer so it was not exposed to sunlight. He found that it actually reacted even without the sunlight. So the uranium rock had something to do with the phosphorescence. So he figured there had to be something in the uranium that reacted with it just like the sun does. So he had to reevaluate his hypothesis and go through more experiments. Very famous female scientists also worked with this, Madame Marie Curie. So she was born Maria Sklodowska, and she was born in Poland. She changed her name to Marie when she moved to France to go to the university there. She was not allowed to go to the university in Poland at that time. So for her thesis process, she studied what they called uranic rays, because so they thought uranium was the only thing that produced these uranic rays like the sun. They later changed the name uranic rays to radioactivity, and Marie Curie came up with this term. Radioactivity is the spontaneous emission of high-energy rays and particles from an atomic nucleus. So this is not a chemical reaction. Radioactivity is a nuclear reaction. So a change in the nucleus. In a normal chemical reaction, the nucleus does not change. Spontaneous meaning it happens all on its own. Nothing has to happen to make this happen. So Marie Curie, from all this work, she was the first person to ever win 2 Nobel Prizes. More people have won multiple Nobel Prizes, but she is still the only person to win one in 2 different areas. She won one in physics and one in chemistry. She discovered the elements radium and polonium. Polonium she named after her home country, Poland. Radium after radioactivity. And then one was later named after her, curium. So it's a nuclear change. It's more complex, like I said, than a standard reaction. So unlike all reactions that we've looked at until this point, there's a nuclear change. So the protons and neutrons actually change instead of just the electrons. Okay, so normally in a chemical change, the electrons shift due to bonding. Here the protons and neutrons in the nucleus actually change. Some of them actually leave or are added. There are different types of nuclear changes, nuclear reactions. You did some of these like alpha decay and beta decay back in 9th grade. So the reason that radiation is helpful and harmful is there's a lot of energy produced from this type of reaction. So the energy can be used helpful in like power plants. We get some nuclear power plant from down by Red Wing. There's a nuclear power plant. Harmful, though, could be things like the atomic bomb or if there is a meltdown in a nuclear power plant, like in Japan after they had the tsunami a few years ago. The energy is Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. And this is related to the law of conservation of mass or energy. Matter cannot be created or destroyed, but it is possible to convert matter to energy. So that's what happens in a nuclear reaction. So just some common types of background radiation. You're surrounded by radiation right now all the time. Not all of it is harmful to you. The biggest source of background radiation, as you can see in this pie chart, is radon. And lots of times radon can be found underground. So there can be radon gas in your home. Some areas have more than others, so this can be very dangerous if you do live by a radon source. You can see we also have medical x-rays can be a source of radiation, so that's why you don't want to have unnecessary x-rays done. Just from the atmosphere and different things, nuclear medicine such as like chemo and radiation therapy for cancer patients. So what elements are radioactive and what makes them radioactive? Any one with an atomic number greater than 83 is all radioactive, so every single isotope is radioactive. There are some that have radioactive isotopes below 83, so anything from bismuth up. Um, for lighter elements, so lower atomic numbers in the periodic table, lower atomic masses, to stabilize the atom so that you don't have a nuclear reaction, it needs one neutron for every proton. So protons, if they're all the same charge, they're going to repel each other. If you put neutrons in there, now that's going to stabilize them because it's going to space them out. The more protons you have, though, the more neutrons you're going to need to stable them, to space them away from each other. So that's why as you get heavier elements, you need more neutrons to balance them out, to stabilize them. When elements become heavy, more neutrons are necessary for every proton to gain stability. So it might not be a one-to-one that you need. Radioactive isotopes have neutron-proton ratios that fall outside the band of stability. So the band of stability, oh, here's a little cartoon for you to enjoy. Little far side. Hope you're laughing. Okay. The band of stability is a graph. So you can see these, the points on here, the blue. That's the band of stability. N equals Z would be your number of neutrons, N, number of protons, Z, when they're equal to each other. So a one-to-one ratio. You can see down lower atomic masses, lower atomic numbers down here, it's like right on the red line. So it's a one-to-one ratio. As you get heavier, though, you can see the band of stability increases. So it actually needs more neutrons to balance out its protons. So just a couple random things. Lower than 83, there are two elements that only have radioactive isotopes, technetium and promethium. So that's why we're never going to talk about those two in class, pretty much because they're all radioactive and we're never going to see them in our area. Oops, sorry, wrong way. Uranium is the heaviest with atomic number 92. Naturally occurring. Ones above this are all made in nuclear research facilities. On your periodic table, you'll notice everything above uranium. The symbols are written in kind of an outline. That's because they are man-made, so you're not going to find them in nature. Uranium was used in the atomic bomb, one of the atomic bombs that was dropped during World War II. It was the bigger one. The other bomb was made with polonium. So another cartoon for you. Enjoy. You're laughing again. So last little bit of this, we'll talk about half-life. Half-life is the time required for half the original sample of particles to decay. So radioactive elements decay at a certain amount of time. Everything has a specific half-life. So after its half-life, let's say it's 5 days. After 5 days, half of it will have decayed. So it always has the same half-life. And half-lives can be in a huge range. You can have some that decompose or decay, very, very quickly in like fractions of seconds, and some take billions of years for half of it to decay. So after that half-life happens, another half-life will occur. You'll just lose the next half. Excuse me. So let's say you have 100 grams to start, and your half-life is 5 days. After 5 days, you'll have 50 grams. After 5 more days, half of what you had left would decay. So now you'd have 25 grams. After another half-life, now you'd have half of that, 12 and a half grams. You're going to get to a point where it's going to get so small, it's going to seem almost like 0, but you can never actually get to 0 because you keep dividing by 2. So this predicts the behavior of large numbers of atoms, but we can't predict when an actual individual atom. We can just say, in this group, half of it's going to decay. We don't know which half. When we talk about half-life in equations and tables and charts and things, we use the lowercase t and then the subscript 1/2 as our symbol. So these are some radioactive isotopes you should know. The first one is cobalt-60. Cobalt-60 has a half-life of 5.271 years. Excuse me again. It goes through two types of decay, and you don't need to know about these right now, but beta and gamma. And they use this to diagnose if you don't have, if your intestines aren't absorbing vitamin B12. So they use this medically. The next one you should know is iodine 125, and this has a half-life of 60 days, so much shorter. So this they use in radiation therapy. They treat prostate cancer with this, malignant tumors, and they also use it as a radioactive tracer. So they can put these in your body, some of these radioactive elements, and then using an x-ray and different scans, they can see where it goes through your body. So they can see if there's blockages or leaks and different things. The next one is iodine 131, so a different isotope of iodine that's also radioactive. It has a much shorter half-life, only 8 days. And this they use to test for and treat thyroid cancer, and then also as a radioactive tracer. And the last one you should know is carbon-14, which I mentioned in the isotopes video. It has a half-life of 5,730 years. They use this to determine age of materials up to 60,000 years old. So you may have heard of carbon dating. So everything that was once alive has, or is alive, has carbon in it. So it has carbon-14. So if you find a fossil of something, an animal or a plant, you can determine based on how much carbon is left, you can work backwards and figure out how old it was based on how much carbon it should have had when it died. So you can do some math there. It only dates materials up to 60,000 years old, though, because after that amount of time, the amount of carbon-14 you have left will be so small that it'll be too hard to detect. So remember I said you're going to keep dividing by 2. Eventually, you're going to get to a really, really, really small number. It's going to keep dividing by 2. It's never going to be 0, but it's going to be too small to measure. So dinosaurs, for instance, we cannot measure how old dinosaurs are with carbon-14, but we can, let's like ancient people, different things like that. We use other radioactive isotopes to date dinosaurs and things beyond 60,000 years. And that's the end of the radioactivity lesson.